So now that we've defined vector spaces and subspaces and the like, it helps if we can relate different components of a vector space to each other. And so this is the realm of norms. So first let's define what a norm is. A norm, and we denote that double bars with something in between, on a vector space S. And here once again we're abstracting out what we've come to know intuitively as a concrete example. But what it does is essentially you give it a vector and it gives you a real number, and there are certain properties. For all x and y in our space. So property number one, the norm is always non-negative. And we only have a norm of 0 if x is the 0 vector. Okay, so second, a few other relationships. One, if we add two vectors together, the resulting norm is going to be smaller than the individual norms of those vectors, and this is the triangle inequality. Now, just a heads up, we're going to be talking about inner product spaces next, and inner products. And inner products have some similar properties, but there are some subtle differences. So it pays to pay attention to whether we're talking about just a norm or an inner product induced norm, like we'll be talking about later. And this is the homogeneity property. Okay, so those are the properties. It's always positive. You multiply it by a scalar is the same as multiplying the before the norm is the same as multiplying the norm by the absolute value of that scalar. Make sure it's always positive. And then we have the triangle inequality. So there are other definitions that we can use kind of to speak about what the norm tells us. And once again, these should be, for the most part, intuitive. We often talk about the length of x, and in a particular, for a particular norm, the length is just, well, the norm. The distance between two vectors, they're also in S, but I'll just leave that off right now, because by this point we understand that is x minus y. Now remember, we didn't define subtraction. What we defined was addition of the negative, but it's the same thing. So we use shortcuts here, and we just call it subtraction. But it's, remember, subtraction is the addition of the negative. And importantly here, a linear vector space equipped with a norm when I see something like that, I think of these free video games that you can buy that have in-app purchases, so you can get a free vector space. But if you want a norm, you have to pay extra. Whoops, I was thinking ahead. So in practice, we don't refer to a normed linear space. I think that's what the course notes say. I usually call it a normed vector space. I think that's kind of more appropriate. So there are a lot of examples in the course notes. I'm just scrolling through them right now, and I see 7. So I'll just cover a few of them so we can discuss, and then you can take a look at those others you know, on your own time, and I highly recommend you do that. So some examples. So when you're talking about a norm, you always have to talk about it in the context of what space you're in. So let's do this first one. Our context is that we are in Rn, and one norm is denoted by this 2 right there, is the Euclidean or L2 norm. And so for this one, you simply sum up the magnitude squared of the individual elements and then take the square root. So this is the Euclidean norm, often called the L2 norm. And this is the one we're used to in physics, really. You have 2 points, x and y, and you want to know the direct distance between them. You can find that by x minus y, like that. Okay, so a common example. Here's another one. We have, once again, we're in Rn, so we can kind of compare these. And common norms have shorthand ways, so we put the subscript 1 there to denote that we have the what we call the L1 norm. It's also called the Manhattan norm, and it's just equal to the sum of the absolute values. So this is L1 norm, sometimes called the Manhattan norm. So why is it the Manhattan norm? Well, it's because if you have 2 points, I'll draw them a little further apart. Say this one and this one, x and y. In Manhattan, you would have to walk along the roads, which are in a grid pattern, and not cut through buildings unless you're Captain America. So in this case, the total distance is the length of the path that you would take. So if we had x minus y on the Manhattan norm, it's just equal to this distance plus that distance. So it's basically x1 minus y1 plus x2 minus y2, like that. This actually, just a few remarks. The L1 norm has been used extensively in signal processing since the early days. The L1 norm is being used more and more. One of the reasons the L2 norm is used so much is, one, it corresponds to what we experience in physics. It is related to our common measurements of power or energy. The Euclidean norm squared would be the energy of a vector if that vector represented some physical quantity such as voltage or height or other things like that. So it has a lot of physical correlates. Not only that, but it's differentiable, and there are some nice properties. The L1 norm has some other properties that are used a lot in things like sparse coding, sparse signal optimization, that really were numerically intractable until recently, and so now they're used a lot more. We can generalize those, the L1 and the L2 norm, into what we call the LP norm, written like this. And in this case, we have n equals 1 to n. And now the question that was on everyone's lips, why with the L2 norm did we have to put the absolute value around it? Because when you square something that's a real number, that becomes redundant. Well, it's because it relates it back to this LP norm. So this is for some value of p, and it can range from 1, oops, that's p, to infinity. LP norm. Okay, so a few things to note. Every once in a while you'll see somebody referring to, or hear somebody referring to, the L0 norm. The L0 norm actually does not follow all the properties of a norm. The L0 norm simply counts how many non-zero elements you have. That's what it does. And this is important in some machine learning and optimization things. We would really like to optimize against the L0, and I'm using air quotes right now, you can't see me, norm, but, well, it's not a norm. And so a lot of the mathematics that we would normally want to use cannot be used. So do yourself a favor, sound educated, and don't ever refer to the L0 norm unless you put quotes around it. It might be better to say the L0 measure. Okay, but that comes up, so I wanted to bring it up. So that's on the one extreme end of the spectrum here, where p was erroneously taken down in its limit towards 0. But what if we go the other way up to infinity? Well, if we, looking at the equation for the LP norm, you could see that if you raised p to the infinity power, or p became infinity, and you raised everything to the infinity power, of course everything's going to blow up and become infinite, or going to go down and become 0, depending on whether it's above or below 1. But that the very largest value of xn is going to be now infinitely larger than any of the others. Well, then when you take the infinite root of that, you get something that is all the ones that were infinitely smaller than n go away, and you're left with just that one value. So that's a long way of justifying why we still call it an L something norm and why it's the L infinity norm. Like this. So if we go back to our diagram with our 2 points, let me put them like this. We have X, and we have Y. The L infinity norm is measuring that distance, but not the vertical one in this case, because the horizontal distance is the greatest distance. Okay. All right. So this next thing is a way of kind of visualizing what goes on with norms, and give this some thought, because in my experience people can misunderstand this. And so I'm going to draw this diamond shape. So what does this represent? Well, this shape is all x1 and x2 for which the norm, the L1 norm, is equal to 1. So it's p equals 1 in this case. And since we're adding up the absolute value of the two things, so we could look at different points. For example, this point we have 1 plus 0, that's equal to 1. At this point we have 1/2 plus 1/2, that's equal to 1. And here we have 0 plus 1, and that's equal to 1. And so there you go. All those points on that are equal to have a norm of 1. All these points have equal to 1. Okay. The next one is this. You've seen this one before. If p equals 2, this is what we call the unit circle, and all points on that unit circle have an L2 norm of 1. So the distance here, we have a radius of r equals 1, so all points on that circle have a norm of 1. So when we get to the L infinity norm, I should make use of these drawing helps more frequently. Okay, so that looks good. Here we have p is equal to infinity, and so we have infinity norm is equal to 1. So incidentally, looking at these two things, it kind of looks like if you were to, just visually, if you were to average a P1 norm, an L1 norm, and an L infinity norm, you would get something that kind of approximates the L2 norm, at least in a piecewise linear fashion. And in fact, that's one of the cheap and dirty ways that you can approximate an L2 norm. If, for example, you're trying to estimate the magnitude of a Fourier transform, you don't care if you're 5% off, you just want to know kind of close where it's at. That's one way to do that. One last thing, I've got just a little room at the bottom of the page. I've already spoken about this, but let's, I just want to put this down so it's in the notes. what if P is equal to 0? Then L0 is not a norm. It counts the number of non-zero elements. So, for example, let's suppose let x equal to 3, 2, 1, or 0, 0. Something like that. Then, and we'll also let a equal 2. Then ax is going to equal 2, but for it to be a norm, this would have to equal that, which is equal to 2 times 2 is 4. So it doesn't work out as a norm. Okay, so there's a quick, easy introduction to norms, and we'll pick up next time talking about inner products. Thank you, and have a good day.